or in three-dimensional case, f, g, and h, are called the component functions of the vector function. Right? That makes sense, right? Because in a vector, you have the x component, y component, z component. So the functions that are in there are called the component functions. So the question becomes, what does a graph of a vector function look like, right? Well, the graph of a vector function, either in two or three-dimensional space, doesn't matter which one, as it takes on these different values of t, these inputs starts spitting out vectors, what you get are all these vectors that live in space, and the tips of those vectors trace out a curve. And so this bit really is a curve. I'm going to show you an example. Here's our first example of a vector valued function right there. And what I'm going to do here is I'm going to see if we can't do it by hand first, and then we're going to use a computer. So I'd like to see what this looks like. So I'm going to create this good old-fashioned, like we're back in, I don't even know what this, pre-algebra. I'm going to create a t-table. This is our input t, and then our output r of t is going to be right here. And I'm going to start with 0, because 0 is always fun, right? Yeah. And let's look at this. This vector valued function has two component functions, right? This component is the f component and the g component. So if first I replace t with 0. There, I square it, I get 0 squared. And then I replace that t with 0, I get 1 minus 0 is 1. Right? And that's a vector in two-dimensional space, right? And then let's do another one. Let's plug in 1. Plug in 1, we get 1, 0. Right? We'll do one more. Plug in 2, we get the vector 4. 2 cubed is 8. 1 take away 8, negative 7. Yeah? Let me draw these vectors in like a standard position. And what we want to do is we want to kind of think of t as being a clock running in the background. So at t equals 0, that's like we're about to start the watch. At t equals 0, we have the vector 0, 1, which is the vector that looks like this. Right? That's our vector 0, 1. Agree that's 0, 1? Yep. Okay. And then that's at the beginning of time. And then let's say 1 second later, we're here, right? That's the vector 1, 0. Like that. And then at 2 seconds, we're at 4, negative 7, which is off the charts way down here somewhere, right? And so we have this vector that comes down like that. If you were to think of all values of t that you could plug into this, you're going to get all these vectors, and you're going to try and see what do the tips of these vectors create. It's going to be like a path through space, right? Through two-dimensional space. Here it is. I'm going to have the computer plug in values for t. The red vector is the output. So here it goes. See that? Yep. So that's all the values of t being plugged in. It starts to create all these vectors. And the tips of those create a curve through space. Yeah? All right. So that is now how we will draw curves in here. We will use a vector valued function.
How would you describe that curve?
It's not quite parabolic because this is not parabolic. So I don't know, it's just a random kind of thing.
Just a curve.
Now this one is really a good one. This is a good one. Okay, look at this one. This is a vector valued function, right? The outputs are vectors in what dimensional space here? 3. Right? Because we have input. Input is t. We have 1, 2, 3 component functions. Think about what happens. You know what? Let's do this. Let's pause on that for a second. Let's look at the two-dimensional. Let's do a two-dimensional vector. This is such an important vector function. Put a star next to this because this is a really big one in this class. So look at that vector function. if you look at this and start letting t be, start at 0 and then start letting t grow, then you can think of this as really spitting out points on the unit circle, right? Because remember, on the unit circle, the x-coordinate is always cosine of the angle, the y-coordinate is always sine of the angle, right? So like at 0, let's say at t equals 0, you get cosine of 0, which is 1, and sine of 0, which is 0. So you would be at this vector right there.
Yeah.
And then if you plug in another value of t, right, you continue to start to draw these vectors that go like this. And eventually they're going to come back around. So you're going to wind up drawing the unit circle, right? That's the unit circle. And if I keep on going, let t keep growing. So you can keep drawing this circle over and over and over, right? And there's an important thing to understand here, that this is still a function. Because you know the vertical line test? That's only when we're talking about functions of one variable. Here we don't have to worry about vertical line test. Think of it this way. Take any 2 points that, if you try and draw a vertical line, those 2 points, do they come from the same input?
No.
No. This one comes from that input, right, for t, which is that angle, and the other one comes from a different angle. And since we don't have a single input going to 2 different places, it's still a function. Yes?
Is this the same as polar?
It's the same as polar, except we're using vectors. Yep.
Oh, okay.
Let's do one change to this. If I put a constant, let's say a in front of this, all that does is changes the radius. And now you draw a circle of radius a. So that gives you a bigger circle if a is bigger than 1, right? So now with that in mind, what does this draw? What's that? Like a spring. So what's happening here is, it's as t goes, the first 2 components are trying to draw a circle, right? They're trying to draw a circle in the xy plane. So it's like we're trying to draw a circle like this. But as time goes on, the z coordinate, right, the z component, I'm sorry, of the vector is going to grow. T over 5 is the same as 1/5 t. And that's a linear function, right? That's a linear function. And so you're trying to draw circles, but at the same time, your z component is trying to go vertical, right, or go up linearly. So you get this thing that slowly spirals up, and you get that. So there it is. I have the computer drawing it for me. As time goes on, it draws that springy looking thing. Coil spring, right? Yes?
So y vectors are not parametric functions?
Y vectors not parametric. They're so intertwined. It's because we want to be able to do things like use our cross product and dot product to find things that are orthogonal. So using the vectors makes sense. Plus, when you use parametric, right, you're drawing points. We're drawing vectors, right? And so, yeah, hang tight, because where we're going to get in this section, I think, may convince you why vectors is just more powerful, or preferred, I should say. Parametrics have their own place, but for here, the vector function is probably better. All right, so now that we've defined a new function, right? Think about your whole life, like what we did. We had functions, you get to calculus, you do limits, right? What do you do after limits? You do derivatives. What do you do after derivatives? You do integration. So that's what we're about to do. It's all in this one section. We're going to have vector functions. What are limits of vector functions? What are derivatives of vector functions? What are integrals of vector functions? And it's not that bad, okay? It sounds terrible. It's actually pretty easy. All right, so first things first. First things first here. Let's define what it means to take the limit of a vector function. So if you're given a vector function, either 2 or 3 dimensional, doesn't matter, then the limit, if you want to take the limit as t approaches some value, then all you have to do is take the limit of each of the component functions. So each vector function will have its own component functions. Just take the limit of each one. And that's either for the 2 or 3-dimensional case. So I have an example because I think it's easiest if I just give you an example. So look at this. I'm giving you a vector function and I'm saying, hey, what is the limit as t goes to 0 of this vector function? So what is the limit as t goes to 0 of this vector function r of t? Well, by definition, all it is a vector. Okay? The limit of a vector function is a vector. And it is just the vector that you get when you take the limit of each of the components. So the limit as t goes to 0 of cosine t, and then the limit as t goes to 0 of sine t over t, and then the limit as t goes to 0 of e to the t minus 1 over t. So all I have to do is just take the limit of each one, right? That's it. Now you have to go back to Cal 1 and see how much you remember about limits. So whenever you do limits, the first thing you do when you calculate a limit is you try direct substitution. You just try plugging in the value of t and just see what happens. So I'm going to let t go to 0. Cosine of 0 is 1.
Yeah.
There's nothing wrong there. 1. Yay. Okay, now I try the next one. Direct substitution. Sine of 0 is 0. Divide that by 0, you get 0 over 0. 0 over 0 is not good, right?
No.
You have to figure out some way around that.
Yeah.
So there's a couple of different options. Hopefully, you remember L'Hopital's rule, because L'Hopital's rule is what I would use here because we have 0 over 0. If you don't know what L'Hopital's rule is, you need to make a note of that and you need to get with me as soon as possible because the bleeding is going to be hard to stop if you don't figure the L'Hopital's rule out. Yes?
It's derivative of the top over derivative of the bottom.
Yes.
Right?
If this limit exists, then it's equivalent to the limit of the derivative of top over derivative of bottom. So I'm going to just use L'Hopital here. I'm even going to state it here. I'm using L'Hopital. Limit t goes to 0. I take derivative of the top, which is cosine t, derivative of the bottom, which is 1. And let's go ahead and just finish that out. Now if I let t go to 0, cosine of 0 is 1. 1 over 1 is 1. And you just get 1. So here's where I am now. Let me put the answer up here. So right now, my first component, the limit's 1. The second component, limit's 1. And then the last one, let's see, t goes to 0. E to the 0 is 1. 1 minus 1 is 0. So we get 0 on top and then 0 on the bottom. So L'Hopital again, right? L'Hopital, limit, t goes to 0. Okay, derivative of the top is itself. Derivative of e to the t is itself. Derivative of 1 is 0, so we just get e to the t over derivative of t is 1. And now let t go to 0 now. You get e to the 0 on top, which is 1. 1 over 1 is 1. So you get the vector 1, 1, 1. There you go. Now, this example was to remind you about limits, right? I showed you how L'Hopital's rule came into play here. I only gave you examples here in class of 0 over 0. But you have to go back to your Cal 1 and remember that there are a bunch of indeterminate forms, right? In a, let me see, I think I have my Cal 1 stuff right here.
Hey, yeah.
Yeah, this is, I can't even see this.
It's with the same mark.
There we go.
as last time, too.
Yeah, so this is the summary. These are all of the indeterminate forms that you can see in Cal 1. 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0. All of those require something, right? And I expect as a Cal 3 student that maybe you don't know right off the top of your head how to do it, but if you're presented with one of those problems, let's say like on a mini exam, that you'll be able to go figure it out. Yes?
So question, if we have your notes from Cal 1, are we allowed to use them?
On what?
A mini exam or a proper exam?
If you're doing a mini exam and you're working alone, I don't care what you use in terms of your own notes and your own stuff from the past.
Okay.
The only thing that you can't use notes on is the midterm and final that you come into class, you can only bring in what I tell you can bring in.
Okay.
Yeah.
So sort this stuff out.
Yep.
Gotcha.
Yeah, and there's stuff like you have to do log, bring in the logarithm to bring stuff out, and there's a bunch of stuff here. I'm kind of like, remember, there's a lot here, okay? So, but in terms of, it's not new, right? The idea of a limit's not new. All right, that's how we do limits. All right, continuity. Continuity. That was the next thing in Cal 1. We talk about limits, and then we talk about continuity of a function. So continuity of vector functions. Given a vector function, whether it be two-dimensional or three-dimensional, then we say the R is continuous at some point A if the limit of the vector function equals the value of the vector function at that point. That's the same definition from Cal 1. In Cal 1, we said f is continuous at x equals a if the limit as x approaches a of f of x equals f of a. That was the exact definition of continuity in Cal 1. This is basically saying the exact same thing. That wherever your limit is approaching, when you get to that limit, it's filled in. Like it's not an open hole or a singularity or asymptote. Yes?
If any of the components are unbounded or undefined, is the entire vector the same thing? If one goes like just infinity, like.
Oh, good question. So what's being asked is, like, let's take this one for example, the one we just did. We're taking the limit as t goes to 0, right? Is this continuous at 0? No. Why? Well, the limit exists, right? What's the limit? We just found it, 1, 1, 1. But what happens when you try and plug 0 in? Not take the limit, but actually plug 0 in. You get 1, you get undefined, you get undefined. So it's not even defined at 0. I think your question was, what if one of these, like two of them are okay, but the other one's not, then that means continuity is out. You only need one of them to go bad.
Right, I'm not talking about specifically continuity, just like unbounded, like t go to 0 for if like 1 over t.
1 over t, yeah.
But that's completely unbounded.
That would mean it's undefined,
Right.
and then the limit would not exist either because you're going to infinity, right?
Right, but so if one of the components.
If one goes bad, it's all bad.
Right.
Yep.
Okay.
All right, where are we? Okay, continuity, we're not going to get deep into continuity. That's just, there's the definition, let's move on. All right, look at this curve right here. Vector function, boom, there it is. Does it live in two or three dimensional space? 3, right? 3-dimensional space. Raise your hand if you think you know what this draws. You think you know?
I think so, a line.
A line. This is a line. How do we know that? Well, we already studied this, right? Remember the vector equation of a line? The vector equation of a line was this R naught plus t times v, right? Where R naught was like a point, well, a vector pointing to one point on the line, and then we had t times v. And so if you look back in our notes, a lot of times that we did it, we broke it down into this form right here, where we had a number, and then some number in front of t, and then a number, and some number in front of t, and then a number, and some number in front of t. And the coefficients, right, -1 here, 4 here, right, and the -6, that's the direction vector, isn't it? That's what we call the direction numbers. So those numbers give us the direction of the line, and then the other number, which would be, what, 1, 2, and then here it would be 0, would be one specific point on the line. So what I'm getting at is we have already looked at one type of vector function, right? Lines can be looked at as vector functions. Do we have time? Yes, we have time. Good. I'm going to get to the example I really want to do, which is a really interesting problem. All right, so this one is kind of a basic problem. There's nothing crazy here. The next example is fun. All right, find the vector function of the line segment from that point to that point. All right, I'm going to go through this quickly because we've done this a couple of times. First thing I'm going to do is write down what the vector function should look like. That's the generic form for a vector function of a line. For us, my R naught is going to be a vector pointing to either one of those points, but they say for me to go from the point 359 to the other one. So I'm going to start with my R naught being that first point because I'm going to the other one, right? So from that first point to that one, that's my R naught. And then I need V, my direction vector. And all I do to get V is create the vector that goes from here to here. So V, right, this is not new, right? We've done this. -8, 2, -12. Y'all agree? It's my direction vector. Okay. R of t should be equal to the vector 359 plus t times the vector -8 to -12. And if I put those together, I get 3 minus 8t, 5 plus 2t, 9 minus 12t. And that is the vector equation of the entire line, isn't it? That draws the entire line. I only want the line segment from here to here. And I told you that as long as you follow my format of letting R naught be this point, the starting point, and creating the V, as the vector that goes from here to here, then to make the line segment happen, all you have to do now is just restrict t between 0 and 1. So this, and then you say t between 0 and 1, and you will draw the line segment from here to here. There's nothing new here, right? This is all stuff we've done. I guess the bigger takeaway would be for us to understand now that that's like our f of t, this is like our g of t, and this is like our h of t. Those are our 3 component functions, right? Those are our 3 component functions. But we're at a point in the class now where these functions can be anything. They don't have to be linear like this. They can be whatever. And then we can take limits of them and everything else. All right, I have 30 minutes. We're not staying late today? No. 10 minutes. I'm going to show you the problem. I want you to think about it. I don't want any responses yet. I just want you to sit there and think about it. I'll read it first. Find the vector function and its domain representing the intersection of these 2 cylinders. Now, we just talked about cylinders, didn't we? Okay. I'm going to give you just a minute to think about it. All right. We're in 3-dimensional space. This is a cylinder. X squared plus y squared equals 9. So it's a cylinder that has a radius. If you're going to talk about a radius, it would be like 3, wouldn't it? Which way does a cylinder, which axis is it going to go down for this one? Z. So it's like radius 3, this beer can, right? That goes forever up and forever down. Yes? We've got that cylinder. And then this cylinder has a radius of 2, but it goes out the x-axis, which is the red one, right? So I've got this, we have the beer can this way, and then we have a smaller beer can cutting through this way. And what I want us to do is find the vector function and its domain representing the intersection of those 2. So I want us to come up with an R of t that draws me the curve of intersection of those 2 cylinders. That sounds hard, doesn't it? You have two cylinders,
Yeah.
and they intersect each other, right? See that blue curve? I'm going to take the cylinders out so you can see it. Right? That's where the two cylinders hit each other, yeah? Come up with the R of t that draws those two blue curves. Draw it. I mean, you have to come up with R of t. Does that seem like that would be hard, or not really? What are you thinking?
Just take the formula for green cylinder, and you log its domain because the.
Wait, say again. Take the lock.
The face of the green sphere is the point of intersection non-closed. So all you gotta do is find the green sphere. I'm not from here, so this weather's not fun.
You don't like Texas weather?
No.
It's impossible to get used to, right?
Yeah.
All right, I think I'm with you. Let's start simple. Let's just kind of come out this way. Remember, the red axis is the x-axis, right? Okay, come out this way, and imagine we are looking at it from way down, like you are, right? You're looking at it straight down right now, and you can see from that direction, what is it that you're drawing?
Circles.
Just circles, right? Just circles. The only thing that's going to change is as you're drawing the circle, right? As you're drawing the circle, you have to stay on both cylinders at the same time, don't you? All right. So here's how we go about this. My R of t is going to be some three-component function, leaving plenty of room here, all right? Now, let's try and draw this circle right here. Like I was saying, you're looking down the x-axis. The big beer can had a radius of what? 3, right? Radius of 3. And then the can that went this way had a radius of 2. Can you draw me a circle in which plane is this? This is the z and the y. Can you draw me a circle in the yz plane that has a radius of 2?
Yeah.
How? You have to use a vector function. Don't give me this. Don't give me this equation. I agree, that will draw me a circle that will draw me a circle in the yz plane of radius 2. Has to be a vector function. So how do you draw the vector function that draws that? We just talked about it.
That would be cosine t, sine t.
Almost. One more thing.
Cosine t.
2 cosine t, 2 sine t.
Yeah.
Right? That will draw me a circle of radius 2. But I need that to be in which? The yz, right? Yz. So watch what I do. 2 cosine t, 2 sine t. See? The y, the z. That by itself, right? That by itself should draw me circles of radius 2 this way. Y'all understand?
Yep.
Everybody? Yes? Yes? No?
It's okay though.
Okay, well, I mean, I could tell,
Yeah,
so.
I have blank look on my face, yeah. No, I-
Okay, well, let's back up, because I want everyone to understand this. Earlier, when I did this, did you follow this when I did that? I said that's a circle of radius 1?
The coefficient just enlarges.
Is just the enlarging. I called it A earlier, but it could be arbitrary, it could be anything. It's like the radius.
And you put it in the y and the place because that's the point.
Because look at this equation right here. That's the one with radius of 2, right? And it has y and z, which means it goes down the x-axis. So here's the x-axis pointing directly at you. Okay, the cylinder's coming at you. What do you have here? The y-axis, right? And the z-axis. So you want to be drawing the circle with y and z, not x and y. Right? If you did 2 cosine t, 2 sine t, you'd be drawing circles this way. You see what I'm saying? Y'all okay with this?
Yep.
So we're drawing circles. Go ahead.
The center of the circle is the free variable, like the cylinder.
For the cylinder, yes. The cylinder just comes back and forth, right?
Yeah.
So let's go back to our picture. From this direction, it looks like we're just drawing circles, right? Now let's look at it from the side. from the side, that's the x, this is the x-axis, right? So if you're on the intersection, looking at it from the side, it's not a circle anymore, right? It's some weird curve. So you need to somehow account for that kind of back and forth that's going to happen, right? As you try and draw your circles, your pen is going to be coming, I'm going to exaggerate this, your pen's going to be coming like out and then back in and then out and then back in. Question?
Would we look at it from the top then and use the
We
fact that it's a circle there?
We actually don't even have to do that much, because do you agree that the vectors we're trying to draw has to satisfy that and this at the same time?
Yes.
Yes? Okay, but let's take a look at this right here. I'm interested in the x component function, right? And so this is already taken care of here and here, drawing my circles. I just need the x to be somehow manipulated as I draw the circles. So I come here, this equation has x in it. I'm going to solve it for x. Right? And square root. Yes? This is what x, well, yeah, I should say plus or minus, because I took the square root. Right? That's what this x coordinate needs to be. But do you know what y has to be? If I'm drawing the circle, right, what does my y have to be? 2 cosine t, right?
Yeah.
So I just write that in here, plus or minus square root of 9 minus parenthesis 2 cosine t, close parenthesis squared. That's it right there. That's your vector function. Now there's two of them. Why are there two? Well, you had an intersection out here, right?
Yeah.
And then the intersection on the other side. And this is going to draw both, okay?
That's cool.
Now, if you don't believe that that does what, well, is there anyone that has a question on how I did this? Yes.
Why didn't you use the hyperbolic to say the domains and put them on both sides? T.
Wait, why didn't I do what?
Why didn't you use the hyperbolic function like you did for the circles? The x squared divided by a squared minus y squared, b squared, and insert that function.
Why would I do that?
Because that's your restriction. You have a restriction on your circles, and you have a restriction on your domain of the circles on the outside. If it's a lot harder than no, but
Well, I can't, these are not hyperbolas. These are circles.
the drawing,
The drawing are not hyperbolas either. I mean, it looks like a hyperbola from the side. Is that what you're saying? Like from here, it kind of looks like a hyperbola?
so that would be your domain, and then your range would be the circles, the height of that.
It's not that simple because, yeah, no, it's not, because we're not looking at this as like our domain is on X. Our domain is on T. T is a clock in the background. It's a little different. I do need to come up with a domain. I'm not going to have time for it, but if I want